Alright, so I'm doing another video working a problem 6.26 out of Griffiths Introduction to Quantum Mechanics, 3rd edition. If you are glad that I'm posting solutions to this or any other material, please subscribe and please like the video. It does help me out and it motivates me to continue to post these videos, which helps me learn the material better and hopefully helps other people too. So this is a long problem. I've tried making the videos as short as humanly possible while at the same time not leaving out key details, and it's going to be hard to do on this one, so this one might be a bit longer, but we'll see. So workout, so this is the Heisenberg momentum. You can see that with this h and the fact that it's a function of time. In this picture, operators vary in time. For the system in example 6.7, don't worry about that. And comment on the correspondence with classical equations of motion. So in that problem, we had a harmonic oscillator, which means that our Hamiltonian was our kinetic part, momentum squared over 2m, plus 1/2 m omega squared, x squared. And the trick for this is, let's say you have any operator Q. I believe this is the equation they give in the textbook. That's related to our Schrodinger operator like this. That's the relationship. So that'll be useful. So let's just go ahead and write that down for our momentum. Nothing crazy, just the definition. Okay. And let's also define our operator U. So our operator U is defined as e to the minus I, the Hamiltonian times time divided by h bar. So this operator we are able to show the exact same way we've shown every operator in this textbook. Very, very similar, just writing out and expanding by Taylor series. But for the purpose of this, I just want to go through the problem. Okay, so we have that, and whenever we have operators, it's very useful to relate our operators to other things, and with the harmonic oscillator, we can use our ladder operators, and we can avoid some of the other means of solving this problem. So the ladder operator from chapter 2 is defined like this. And minus plus I p hat plus m omega x. So in the example problem that it mentions, it has you do this with x. And it's very similar, but now what we're going to do is we're going to try to find our momentum p. The way we're going to do this is as followed. We're going to take the raising operator and subtract from that the lowering operator. We're doing that because we actually want to cancel out the x and be left with our momentum. So that's why that's what we're doing. So this would be 1 over 2 h bar m omega. And then we'll have minus I p hat plus m omega x. And now we're subtracting it. So now we're subtracting it, and now this will be positive. So the reason we're subtracting it is now that these momentums are going to have the same terms, and they're not going to cancel. So we're just going to do a little bit of math here, and I'm going to multiply over by, so when we distribute this, you're going to get minus IP minus IP. Oh, this is square root, right? So that'll actually just be 2. And then you'll get, when you distribute this, a plus and a minus. Those are the same terms. Those are going to cancel. So you'll have your ladder operator is, in that case, just going to be equal to minus 2IP over all this stuff. And we're going to multiply over. So 2 h bar m omega. And real quick, it'll actually just be h bar m omega, because we can simplify that and divide by that. And I'm referring to this 2. So this is just root 2 in the numerator, and then we divide it over. Our ladder operator equals minus I p hat, and then if we divide over by minus I, that's the same thing as multiplying by just I. So okay, then we have our momentum operator in terms of our ladder operators, and now we're going to substitute that into the equation we had along with our U. So P h of t is equal to E. So that I becomes positive because it's the complex conjugated transpose. We have what we just found for momentum. Okay. And then we have just our normal U, not complex conjugated. And then psi sub n of x. Forgot, I should multiply both sides by psi sub n of x. We can also do this. There we go. There we go. Okay, so we did all this. And now, if we think about this operating here, we know what the Hamiltonian operating on our wave function does. It just gives us our energy. We know that this is just this. We know what the Hamiltonian does to the wave function. So we can do that. And that's going to turn into just a constant, as is this. This is just constant. So I'm going to move all that stuff up front. We'll get I h bar m omega over 2 square root e to the minus I e sub n t h bar e to the I h t over little h bar. And then our ladder operators, again, we have to be very careful with operators, psi sub n of x. So it's important we had our e operate on that first. Order matters with operators. And now we need to remember what our ladder operators actually do. Okay, so if we have the raising operator acting on some state, you're going to get n plus 1 square root times n plus 1 the state. And the lowering operator on a state gets you just the square root of n, and then it lowers it one level. So that's what the raising and lowering operators do, and that's exactly what it's going to do to our wave function. So let's apply the operators, the raising and lowering operators, to psi. And it's getting a little late for me, and it's raining outside, so I'm a little tired. Hopefully I'm not making many mistakes. I get very, very sleepy when it rains, so might be bedtime soon. And then we still have our Hamiltonian. Again, order matters, so the Hamiltonian just kind of has to chill while these guys operate. And we know what that does. So this is your raising operator, and this is your lowering operator, just like we talked about before. And now, and only now, will the Hamiltonian operate on these new states, these raised states, and this lowering state. Let's go back to black. Okay, so we still have our constants out front. I would be kind of surprised if I didn't make some silly error somewhere, but we'll see. Okay, so we're the n plus 1 square root, that's not going anywhere. And again, the Hamiltonian, it's just going to get us that state, in this case n plus 1t over h bar, and that same state back. And I e to the n minus 1 t over h bar, and this other state back. Okay, so that's just the Hamiltonian operating on the wave state there. Okay, so this is good. And now what we're going to do is we're going to distribute this guy, it's been here for a while, into what we have, which are now constants, so all is well. And we still have our constants out there, we can't forget about them. Okay, so we're going to get n plus 1 square root e. They both have an I, they both have a t, they both have an h bar, and that'll be n plus e to the n plus 1 minus e sub n. And then we still have our state. And likewise, this does not change. We're going to factor all this stuff out. Oops. We're going to factor all this stuff out, and you'll get, we'll factor out a negative. Okay. So this is good. This is good, and we have our state here. Okay. So e to the n plus 1 minus e sub n is just e, right? If we're subtracting n levels from that, you're only going to be left with just e, the first one. So hopefully that makes sense. And likewise with our other term, e sub n minus e sub n minus 1. You're subtracting everything but one term. So essentially what I'm saying is this is just e, and this is just e. Okay. And e is just h bar omega. So let's plug that in. Hopefully everything makes sense so far. Try not to skip too many steps. Okay, so if we plug in h bar omega, the h bar will cancel and we'll just get I omega t. And minus the square root of n e to the minus I omega t. Okay. So now what we want to do is we actually want to plug our ladder operators essentially back in and factor out our wave function. So I'll show you what that looks like, because we ultimately want to get rid of this psi, and we can't do that because these are different states. This is one state up, this is one state down. So I'm going to rewrite it, and I think you guys will see what I'm doing, and I'll talk about it as well. Okay. So I'm going to rewrite this like this. E to the I omega t, the raising operator, minus e to the minus I omega t a minus, operating on psi n of x. So think what happens if we distribute it. First off, these are not affected by our ladder operators, so the order for that you can be a little more lax. But think about what happens if you were to distribute this psi and allow the raising and lowering operator. Well, you're going to get an n+1 for the first term, and it's going to go up a state. And for the second one, you'd get a minus n and the state below it. So I've just rewritten this in terms of our raising and lowering operators. Hopefully that makes sense. And I did that for this very reason, in case you're like, why'd you do that? Well, so I can do this. Okay. All right, so this is a very good start. And now, again, our raising operator, let's define, well, it's already been defined, but I'll write it down again because it's way up there. This is our raising operator. And this is our lowering operator. Okay, so that's just for harmonic oscillators, nothing crazy there. And what we can do now is we know what our raising and lowering operator is, and we know what that is, so these can be substituted in like that. Okay, so we're going to do that. Because this video is already probably getting a little long, I don't really want to skip the algebra per se, but essentially what you're going to do is you're going to get an I h bar m omega over 2 square root times 1 over 2 h bar m omega square root. Okay, so that's just these common factors they all have. And then you would have your e to the I omega t, and then replacing that with what we have left. And then you'd have an e to the minus I omega t. We'll replace that with the I p hat plus m omega x. Hopefully you see that these drop, and root 2 times root 2 is going to get you just a half. Okay, so those are common factors. They're in both the raising and lowering, so that simplifies it. So you get 1/2 I, and then we could distribute this, but I'm going to go ahead and just factor out the common I. So you would have e to the I omega t from distributing in here. You'd get your negative back, plus e to the minus I omega t coming from here. Okay. And then we're going to have our p hat on the outside. Again, the order matters. The p's outside. And then for the m omega x, not really. Not really, because x is, it doesn't matter its position. So just factoring out what they have in common. And now what we need to know is how you can write cosines and sines in terms of exponents. So cosine of omega t is e to the I omega t plus e to the minus I omega t over 2. And sine of omega t is equal to, pretty similar, e to the I omega t minus e to the minus I omega t all over 2. All right, and you can see if we multiply these guys by 2, this fits in here, and that fits in there. Okay, so we can do that. So PHT is 1/2 I. Okay. And then we're going to have a minus I. And this will be multiplied by 2 cosine of omega t momentum plus m omega times, should be an m omega x. There we go. Times 2i sine of sine of omega t. And just for principle, let's do this. Let's move the x over here, because technically it could be from the Heisenberg picture. So let's do that. Okay. And now you could distribute this, and what we're going to get is, so we just distribute the 1/2 I. Obviously the i's will be I squared, so that'll be 1. The 2's will drop, and we're going to get p hat cosine of omega t, and then your 1/2s are still going to drop, and you'll get minus m omega x sine of omega t. Okay, so that's good. And then usually what we do is we call this pH0 xh at 0, or at that time at time equals 0, where our operators are at time equals 0. Okay, so this is all good and wonderful. And that is the answer. That's what we're looking for. Hopefully that makes sense. It was a long, tedious problem, and if it did, please give a like and subscribe. Thank you.